In this section 3.2, we're going to cover the basic differentiation rules and rates of change. In the last section, we just looked at finding the derivative of a function with a difference quotient, and we sort of tied that into slope. Here in the graph down at the bottom, I have this red line, and if I asked you to find the slope of that, you could pick out any 2 points on that line, determine the rise and the run, and figure out the slope. And that slope is consistent for the entire line. The slope at this point is the same as the slope at this point, is the same as the slope at this point, and so on, because it is a linear function. But into calculus, we get more into these curved functions. And when I say, what is the slope at this point? Of course, if we look at the tangent line, it's going to be definitely a negative slope going downhill. Somewhere along here at the bottom of this parabola, there is going to be a point where the tangent line will be horizontal, and that would be a zero slope, a different slope. And as we work our way over here, now we're going to have, of course, positive slopes. And every point has a slightly different slope. So the slope of a line is consistent across the whole thing. When we talk about a slope on a curve, that's more of what's going on at a single point in time. It's an instantaneous rate of change, the change that is occurring at this one particular point. Because the rate of change at this particular point is different, and the rate of change at this point is also different. So most of this section, we're just going to come up with some of these rules for derivatives. The constant rule, the power rule, the constant multiple rule, sum and difference rules. And then we'll even look at the derivatives of our favorites, the sine and cosine functions. Alrighty. First, the constant rule. When we are taking the derivative of a constant, it's just going to be 0. In section, well, this is a little off, it'd be 3.1, that was a previous section. You use the limit definition to find a derivative. In this and the next 2 sections, you're going to be introduced to several differentiation rules that allow you to find derivatives without the direct use of that nasty limit definition. So here in our first theorem box, 2.2, the constant rule, the derivative of a constant function is 0. That is, if c is a real number, then the derivative with respect to x of that number is 0. And it does say see the figure. Graphically, I think it makes a lot more sense here. If I told you to graph the line y equals 3, or we could use the different notation f of x equals 3. Well, if you were going to graph this, if you think back to y equals mx plus b form, there is no x term. That would be 0x plus b, or 0x plus 3. So we'd just go up to the height on the y-axis at 3, and we would have a horizontal line. Y equals 3 is a horizontal line. If I wrote y equals 10, that would be another horizontal line at the height of 10 on the y-axis. And if we look at this line here, this horizontal line, what is the slope of a horizontal line? Of course, it's 0, no slope. So if I asked you to say, find the derivative d dx of 50. Well, that would be 0. Or the derivative with respect to x of pi. Now remember, pi is just a number, 3.14. You take the derivative of a constant, it's going to be 0. And let's see what it says down here under the picture. Notice that the constant rule is equivalent to saying that the slope of a horizontal line is 0. This demonstrates the relationship between slope and the derivative of a function. In example 1, use the constant rule. So here's our function, y equals 7. The derivative, dy dx, is going to equal 0. Here's a slightly different notation. Instead of y equals, they have f of x equals, so we can use different notation for the derivative. Here's f of x is 0. Well, the derivative, f prime of x, the derivative of 0 is just a constant. Its derivative is also 0. S of t is equal to negative 3. So we find the derivative s prime of t, and of course that's going to be equal to 0. And here's a different one, y equals k times pi squared, where k is just a constant. K is just a number. And don't forget, pi is just a number too. We can take our calculator and punch in 3.14 and square it and get 9 point something. And then multiply that by some constant k. It's just going to be some number. So the derivative of that, y prime, is going to equal 0. Okay, and next, before we get to example 2, we're just going to go over a little bit the expansion of a binomial. You might have saw this in pre-calc or algebra 2. It's just a neat little way to find the coefficients when you're expanding a binomial raised to a high power. And we're going to start off by making our little triangle. We'll start with a 1 at the top, and then we'll go down here and here, and we'll have 1 and 1. Now for the next row, we bring the 1's down. And then the middle number is this plus this. 1 plus 1 is 2. And let's do that again. Let me change to a different color here. We're going to bring the 1's down, and then we're going to add these numbers together to get our new coefficients. So we bring down the 1. 1 plus 2 is 3. 2 plus 1 is 3. And we bring this 1 down. And let's do it one more time. So all these are going to come down and or get added together. So we have our 1 at the end. 1 and 3 is 4. 3 and 3 is 6. 3 and 1 is 4. And we bring down the 1. Now this is just to find the coefficients that go in front of our variables as we expand it out. This 1 and 1, that is like, well, let's stick with our calc notation, x plus delta x to the first power. Since it's first power, we just drop the parentheses in the exponent, and the 1 and 1 are the coefficients in front of x and delta x. Now the next one would be x plus delta x quantity squared. And this is an easy one. If we FOILed that out, we would get 1 x squared plus 2, these two terms multiplied together, x times delta x, and then we'd have our plus 1 at the end. And there's our coefficients, 1, 2, 1. 1, 2, 1. And we could do it again for x, not x squared, x plus delta x quantity to the third. Well, the first term is going to be cubed, so we're going to have our 1 x to the third, and then plus our coefficient from our little table here is 3. And then we'll take here it was x to the third delta x to the 0 power. So now this power will go down 1, and it's x squared, and our delta x to the 0 becomes delta x to the first. And then we'd have our plus our next coefficient 3, and now the x goes down another power, x to the first, and the other term goes up a power, delta x squared. And then plus our last term is delta x quantity to the third. Delta x quantity to the third. For the last one, I'm not going to expand it out all the way because I'm just interested in the first couple terms. So here's the fourth power. We're going to have 1x to the fourth plus our next coefficient is 4, and then we drop this power by 1. That's down to x to the third. Delta x to the first power. I think I got that right. Yeah. And then the terms would continue on. There'd be a 6x squared delta x squared. Remember when we did our difference quotient, our numerator was f of x plus delta x minus the original f of x. So here what we did, this binomial expansion, was sort of this part. And when we subtract the original function, let me switch over to red here, we're going to have all of this, and then we're going to subtract our original function. So here we're going to subtract an x squared. For this next layer of the binomial expansion, when we subtract the original function, we would have a minus x to the third. And for the next one, a minus x to the fourth. So when we subtract that second part of that numerator, it always wipes out the first term. And then another thing that we do is, remember this is just the numerator, we're dividing by a delta x. When we collect up all our terms and we divide out a delta x, this first term here, since we canceled this one out, has a single delta x, and that gets canceled out. In the next binomial expansion, this delta x to the first would be crossed out, just leaving the 3x squared. In the next one, this delta x would cancel out, and we're left with 4x to the third. Every term after these, even after we cancel out one delta x, they still have at least a delta x to the first power in each term from here on out. When we apply the limit and delta x goes to 0, all the later terms go to 0. So here's the interesting part. Actually, well, let's just get right into the power. If you notice here, it's now just 2x to the first, 3x to the second, 4x to the third. We're going to be able to generalize that into the very useful calculus power rule. If n is a rational number, then the function f of x equals x to the nth power is differentiable, and the derivative d dx, the derivative with respect to x, of x to the some power becomes this, n times x to the new power of n minus 1. For f to be differentiable at x is 0, n must be a number such that n minus 1 is defined on that interval containing 0. Just a real easy example here. Let's just say x to the 7th. Y equals x to the 7th. I want to find dy dx, or y prime. I want to take the derivative of this. Well, the power rule just says bring this exponent down front. That becomes your coefficient. That n up here move down front. So this becomes now 7x. And this power is now reduced by 1. Our formula says n minus 1. So that 7 drops down in front of the x. And this 7 drops down 1 power to the 6th power. That's our derivative. That's the power rule. And you can sort of see how this comes in with the binomial expansion. This was a quantity squared. X squared became 2x. Here was x to the 3rd, and that became 3x to 1 power lower squared, 3x squared. X to the 4th became 4x to the 3rd. Alrighty. Okay. So let's apply this. Example 2. Use the power rule. And actually, it looks like I should have left myself a little more room here. So use the power rule. Let's see here. Part A. F of x equals x to the 3rd. Oops, that's not a very good looking 3. So we take the derivative. We'll use prime notation here. F prime of x equals 3x squared. I always like to think about deriving as a downward process. Derive down. You know, because they start with the same letter, derive and down. And everything is working its way down. The exponent moves down to become the new coefficient in front of the variable. The exponent moves down one number from a 3 to a 2 in this example. So derive down. Part B. G of x equals x to the 3rd root of x. And because, you know, those radicals can be a little confusing, let's rewrite that as a rational exponent. That would be x, remember there is an implied 1 in here, x to the 1/3 power. So that's our g of x. Well, then what's g prime of x? Well, we follow the same pattern. Bring the 1/3 down front of the variable. So 1/3 x. What's our new exponent? Well, we subtract 1 from this. 1/3 minus 1 is negative 2/3. And usually in math class, you know, leaving exponents as negatives is bad math manners. So we want to get rid of that negative 2/3 exponent. So we are just going to have to manipulate this a little bit. You know, this is 1/3, so we're going to leave our 1/3. And this x to the negative 2/3, remember if we move that down to the denominator, because here it's technically with that numerator, if we move it down to the denominator, it becomes a positive exponent. X to the 2/3, and now make sure that's all in the denominator underneath your fraction line there. So our derivative of x to the 1/3 is 1 over 3x to the 2/3 power. And I guess if you wanted to, if you don't like those rational exponents, you could rewrite that as a radical. That would be x, the 3rd root of x squared. However you would prefer to write it. Okay, and we got one more to go here for part C. Let me clear out a little room here. Part C, they're at y equals 1 over x squared. Well, all right, let's get rid of that being in the denominator. Let's bring it up and write it as a negative exponent. So 1 over x squared becomes x to the negative 2. You know, there is an implied 1 there. When we move that up, we just change the exponent to a negative, and we'll just drop the 1. So we have now y equals negative, or x to the negative 2. So y prime, the derivative, we bring the exponent down front. It's now the coefficient. Negative 2x, and we want to drop this by 1. Negative 2 minus 1 is negative 3. And again, it's bad manners to leave that negative exponent there. So we're going to move that x to the negative 3rd down to the denominator. Now be careful. This negative 2 does have its own exponent. That's negative 2 to the 1st power. This would be a completely different problem if we had this in parenthesis as a quantity to the negative 3 power. But they're not in parentheses. So this is negative 2 to the first. The only thing that's going to drop to the denominator is that variable with the negative exponent. So we have negative 2 over x to the third. And that's our derivative. All right, that's example 2. Let's see what example 3 has here. Now, find the slope of the graph. Find the slope of the graph, f of x equals x to the fourth, when x is negative 1, again when b is 0, and again when x is positive 1. You know, if we did this by the difference quotient and FOIL and all that out, it'd be, you know, a pretty time-consuming problem. But now with this new power rule, we'll make nice short work of this. So our function, f of x is x to the fourth. Even-powered functions are parabolas opening up. So we can see here we got an idea. We know roughly what the shape is going to be. It's going to, you know, if it was just squared, it wouldn't be quite so bottomed out here. But let's take our derivative. F prime of x is going to be 4x to the third power. Remember, this is our position function. It tells us the height we are at for any given x coordinate. This is our derivative. It will give us the slope at a given point. This will tell us the instantaneous rate of change occurring at any x value we want to plug into the derivative. All right, let's check these out. So first they want us to find, actually, this is part A. They want when x is negative 1. So we want f prime of negative 1, and that just means we plug a negative 1 in here. 4 times negative 1 to the third. Well, a negative to a odd exponent is going to be negative, so this will turn into a negative 1 times 4 is negative 4. Part B. They want x is 0. Well, f prime of 0 would be 4 times 0 to the third, which is 0. And lastly, for part C, they want when x is 1. F prime of positive 1 is going to be 4 times 1 to the third, and that is equal to positive 4. Now, does that make sense? Does the graph back up what we found here? Let's look at the first one. X is negative 1. So here, x is negative 1. If I plug that negative 1 into the original position function, negative 1 to the fourth gives us our height, or our position in the coordinate plane. So this point is negative 1, comma 1. Now, at this point that I just highlighted in blue here, what's the slope? Well, we plugged this same x value, negative 1, into the derivative, and we got an answer of negative 4. So at this particular point, our slope is negative 4, nice and steep downhill. For the next one, f of 0. Well, if we plug 0 here into the original function, 0 to the fourth is 0. And if we plug that same x is 0 into the derivative, it tells us the slope occurring at that point is also 0. If we were to draw a tangent line right here, it would be horizontal, where it's touching that graph. And last, when x is 1. If we plug 1 into the original function, the position function, 1 to the fourth is 1, so that's our position in the coordinate plane. But what's the slope occurring at that point? Well, we plug that same x value now into the derivative, and we get an output of positive 4. So here our tangent line would be nice, steep, upward sloping line, a slope of 4, up 4 over 1. Okay, and in this last, this will be the last example we do in this video. This is a real common theme in calculus. Find the equation of the tangent line. They just don't want us to find the slope occurring or anything else. They want us to come up with the entire tangent line's equation. And my favorite, of course, is y equals mx plus b. mx plus b. So here they're giving us a function of a parabola. X squared is a parabolic curve opening up. And they want us to find not just the slope occurring at this point, they want the equation of this line, and I'm going to put it into the form y equals mx plus b. Well, what do we need to write the equation, dang it, of a tangent line? We need two things. We need a point and a slope. So slope is the m, and we need a point to help us find this y-intercept. So we need a point and a slope to write the equation of a line. So let's see here, and they want to find the equation of the tangent line for this graph, f of x equals x squared, when x is -2. So first let's find that point. We know that -2 is going to be our x-coordinate. So it's -2 comma something. We need this y value. How do we find that y value? By plugging our x value into the original function, into the position function. So we plug that -2 into x squared. -2 squared is 4. And if we look at the graph here, over to -2, up to 4, there's a point that's on the graph. So that's the point we're going to need to write the equation of our tangent line, because that's the point where our tangent line is actually tangent to the parabola. Next, we need a slope. How do we find slope? We use the derivative. So our function is f of x is x squared. Well, then f prime of x is equal to 2x. And if we plug that same x value, -2 goes in here. 2 times -2 is -4. So our slope is -4. And now we can write our equation. Let's see, what would be the easiest way to do this? We might start out with that point slope. Y minus y sub 1 equals m times x minus x sub 1. And we have the x1 and the y1 and the slope to plug into proper places. So y minus, our y coordinate was 4, equals, m was our slope was -4. And then we have in the parentheses, x minus, our original x coordinate was -2. So it's minus a -2, and minus a negative turns into plus. So let's clean this up and put it in slope-intercept form. Here's our y minus 4 equals, distribute the -4. -4x minus 8. And then we're going to add 4 to both sides to get y alone. Y equals -4x minus 4. There's the equation of the tangent line that's tangent to this parabola at the x value of -2.